Webb can reach out to the most distant galaxies. It can actually teach us a ton about how this expansion happens at different positions, at different times even. So yes, definitely, it will allow us to peer into details that we have not had the chance to before, for sure. Yeah.
So one thing that I think is really cool is how we tend to use different telescopes. We use data from multiple different telescopes to get an even bigger picture of the universe. So will Webb be complementary to any of the other space telescopes that are already out there, or that might be coming up in the future?
Alex, you want to take this?
I mean, absolutely. You can already put Hubble and Webb images side by side, and you see that there's additional information that you can get from both of those images. And in terms of studying the scales of the universe and dark matter and dark energy that we were just talking about, the LIGO mission, the LIGO telescope that measures gravitational waves, it has found some incredible pairs of rotating neutron stars that helps us understand Einstein's original equations. Webb has the ability for when a unique phenomenon like that happens, Webb has the ability to stop what it's doing and go look at that to provide additional information. And there's actually a system between telescopes where they can alert each other to say, there's something really important and timely going on in the universe. Let's look at it together to get added information. And so Webb will be part of that as well.
So telescopes can phone a friend, and oh my gosh, that's amazing. That is a fun fact. So Wait 1 Minute on Twitter asks, how do scientists separate stars from galaxies in such pictures?
Well, the structure tells you a lot about that, first of all. The fact that galaxies are, we have a name for them, diffuse sources or not. I can't remember actually now the word. But we know which sources are like galaxies or more diffuse, while stars are very, very pointy points in the images. There's a point, though, in which, especially for the faintest stars, in which it gets kind of tough to separate between them just from an image. So you have to go and get more data. There's a point in which it gets challenging, but for most of them, we have a pretty good idea on how to do that.
I actually have a great follow-up to that. So Aerononis on Twitch asks, how do you convert the data into such colorful photos?
Ooh, you want to take this?
Sure. The data come down, as ones and zeros. But basically, what you do is you focus on one color of light at a time, and on your infrared detector, you say how much light is being collected on any given point on the detector. And so you actually have a spatial map for where the light is coming in, and the more light you get, the brighter it is in that one wavelength and that one color. And then we take many color pictures, individual wavelengths, and then add them together to make color images.
It's a process on its own. It's a whole art. We have experts in-house back at Space Telescope that did all this, and seeing this work unfold, unfold the universe, was magnificent. How we humans can make this happen, these beautiful images, it's a whole process that I loved. Yeah.
It is, and I'm glad that you said that, and you alluded to it earlier about how Webb is truly an international mission. Didn't over hundreds of scientists and thousands of engineers work on this mission?
Over 20,000 people make this mission happen. So it's a huge team effort, right?
Mm-hmm. And now over the next year, there's over 1,000 people who are scientists who are going to use the data. And that's just people who already know they're going to use the data, and there's going to be a lot of more people who jump on it. It has only been possible with an international collaboration in all of these people, and it will, its legacy will extend, and the scientific discoveries will extend as more and more people, and really the next generation of scientists, take this on as their mantle.
Speaking of the next generation, we have Alex, who is 12 years old, who asks, what is the maximum distance that Webb can see?
Good name, Alex. So Webb, we anticipate that Webb is designed to look back about a light travel time distance of 13.6 billion years. So to within about 150 million years of the Big Bang. And it's hard to like put these numbers in perspective. Hubble has seen to about 400 million years after the Big Bang. And out of the age of the universe, which is 13.8 approximately billion years, Hubble has seen maybe like a 2-year-old out of the entire age. Webb is going to be able to see a 1-year-old or a 9-month-old. And Nestor and I have young children. We can tell you that there is a ton of change that happens between 9 months and 2 years. And so understanding the beginning of the universe is going to be, you know, really, really amazing with Webb.
That is so exciting. And so our next question is from Tony Jebson on Twitter, who asks, do we know how deep in the atmosphere of WASP 96b the clouds and haze are?
Yeah, actually, we have some calculations on that. I mean, I could tell you the pressure or the height, but I don't think it makes you know, it's gonna make much sense to say it here. But we do, and that's information that it's embedded in this beautiful spectrum that you're seeing here. We know the exact location where the cloud actually starts. We know that it has to go below a certain pressure. So we know like a little bit of the structure of the atmosphere. So yes, I mean, that's the kind of information you get from modeling data like this.
That is so exciting. And so we have Megan Carroll on YouTube, who asks, regarding the fantastic image of the dying star, would the supernova of one star cause the destruction of the other? So I believe there are 2 stars in that image. And how large is that explosion?
So that's a good question. There are 2 stars in this image, and the one that you actually can see that looks brighter, that actually has the strong diffraction pattern, that's actually still alive and well. It's a hot star. The one that only really appears in the mid-infrared image, that's the star that has died. They do gravitationally exert a lot on each other, but the explosion, and in this case, it wasn't quite a supernova. It wasn't quite as massive a star enough to make a supernova. But the explosion from the death of the first star, the material will pass by the second star, but it's not going to perturb it. However, the structure that you see and the fact that it's not just, you know, a pure circle is because of the gravitational interactions between these 2 stars. And actually, what we learned from this image for the first time is that the star that died actually still has dust around it. It's dusty, which basically means it either didn't expel all of its layers, which is which would be really unique, or it might be pulling material from the other star. Anyways, we don't know yet, but they're definitely interacting in more ways than just gravitational.
Wow, a lot of mysteries to unpack there. So that's really cool. We have Armed Camp on Twitter, who asks, the pictures that we're seeing from the Carina Nebula, how old are they? And how many years ago did what we're seeing actually happen? Guess how many light years away was that nebula captured?
I don't have that off the top of my head.
Yeah, me neither.
That's okay. Armed Camp, that information is on nasa.gov in the web feature for that image. Yeah. But I think that does bring us to another good question. Can either of you put into context how big a light year is?
Sure. I mean, you all play with lasers, right? Like these laser pointers, right? So, you know, if you point a laser pointer to an object that is 1 light year away, it will take 1 year for that ray of light to get there. So if you were trying to, you know, share Wi-Fi with your friend at 4 light years away, it will take 4 years for them to actually get your Wi-Fi signal. So you don't really want to do that, right? It's like a very, very slow process. Yeah, but that's basically what a light year is. It's the amount of time that takes, it's the distance to which light can travel basically in 1 year. Yeah.
And to give you another sort of piece to measure it on, pun intended, the light travel time between the Earth and the Sun is 8 minutes, and that's 93 million miles. So 8 minutes into an entire year is a lot more than 83 million miles.
Yeah, I was like, I'm not even going to try to
No,
do that
I-
math. It is just a lot more.
It's a very large distance.
Yeah, that's good to know. We have Pyro on YouTube who asks, will JWST help us identify habitable planets? And so I know we've talked a little bit about how we can study the atmospheres, but we can study more than just water vapor, right? There are multiple different molecules. How does that all play together?
Yeah, so we're going through these questions through layers. The thing to understand is that our planet, in the habitable conditions for our planet, are very far away from our host star, the sun. Because the sun is relatively hot to most stars out there. But the stars that we're going to be exploring with Webb, they're typically very cold. So in order to feel the same heat, just as a radiator, you have to get closer. So the planets that we're going to be studying that have what we call in the habitable zone, that receive heat similar to what we feel here on Earth from the sun, they're much closer